Welcome to week 4 of the AI planning course. We've already seen a lot of material. In week 1, we've seen the basic planning problem and the context in which planning takes place. In week 2, we've learned about the A-star search algorithm, that is the foundation for state space forward search, the algorithm we have seen to solve planning problems. In week 3, we've had two main topics, plan space search and HTN planning. In plan space search, we have described a completely new and different search space, which we can also search. And this was the space of partial plans. Then we have seen how plan refinement operations can be used to define steps in this new plan space that we are searching. And finally, we've seen an algorithm that is basically the UCPOP planner, which is a partial order planner that performs a plan space search. Then we've gone over to HTN planning. HTN planning is a completely different way of looking at a planning problem, so it really solves a problem that is different from the one we've solved with strips-like systems. In this problem, we're not trying to achieve goals, but we're trying to accomplish tasks. So we're using methods to decompose tasks into finer-grained tasks until we reach the level of actions that we can use to form a plan. So that's what we've learned in week 3. And now I want to encourage you again to use the social platform that we provide. And this time I briefly want to talk about a virtual world meeting space that we provide in Second Life. And I hope you will have a look at this and send your avatar there and talk to other people in this space. And I'll quickly go there now, just to see what's going on there. And see who's there. That's Austin's avatar. Hello, Austin. Hello.
The GraphPlan Planner addresses the same planning problem as the Strips Planner or UCPOP. That is, the planning problem consists of a set of operators constituting a domain, an initial state, and a set of goals that need to be achieved. One major difference to the planning algorithms we've seen so far is that GraphPlan works on a propositional representation. That means the atoms that make up a world state are no longer structured. They don't consist of objects that are related to each other, but of individual symbols, where each symbol represents a fact about the world that can be true or false. The same goes for actions. They are now individual symbols, not parameterized actions. But as it turns out, this isn't such a major difference, as every strips planning problem, as we have seen it so far, can be translated into an equivalent propositional problem. So, for simplicity, we will now think of the planning problem as given in its propositional form. And here is now an overview of how the GraphPlan algorithm works. The details of this will follow in the remainder of this segment. Essentially, what the algorithm does is create a data structure called the planning graph, an example of which you see here. The algorithm then consists of two major steps. The first step expands this planning graph with two new layers, an action layer and a proposition layer. The second step of the algorithm searches this graph for a plan. And here is how the first step works. The algorithm starts with a single layer of nodes in its planning graph, and that is the proposition layer P0. In this layer, we have all those propositions that were true in the initial state as nodes. So in this layer, we have 6 nodes holding one proposition each that were true in the initial state. That's the initial planning graph. The graph expansion step then adds exactly one action layer and one proposition layer to this graph. The first action layer contains all those action symbols, those 4 here, that would be applicable in a state consisting of all those symbols contained in the preceding proposition layer. So these actions are applicable in a state that would consist of all these symbols. And then in the proposition layer P1 that we're adding in this expansion step, we have all the effects that were asserted by the actions in the preceding action layer, plus all the propositions that were true already. So this is the proposition layer P1, consisting of all the positive effects of these actions. and all those elements that were already in P0. The edges you see here simply represent the preconditions and effects of the actions. When we look at the detail of the algorithm, we will see that there are actually a few more action nodes in the action layer representing no operations, which were introduced to carry propositions forward from one proposition layer to the next. And there are also some additional edges not shown in this graph, and these are edges that are internal to proposition and action layers and represent mutual exclusivity of these symbols being true. One important feature of this expansion step that comes first is that it runs in polynomial time, so it is fast. The expansion step is then followed by the second step in this algorithm, which is the backward search. So what we do in the backward search is search for our plan from the last proposition layer in the plan. So we are searching from this layer here, and we're going backwards towards the initial state until we reach the initial state, and search for sets of actions that may constitute our plan. And this is a standard search following the type of search we have seen before that can be done with something like the A* algorithm. Unfortunately, this means that the backward search may have exponential time complexity. If the backward search finds a plan, then we're done because we've solved the problem. If it doesn't find the plan, then the algorithm returns to the expansion step, so it generates a new action layer, which is shown here, and a new proposition layer, shown here. And this is again followed by a backward search, starting from the last proposition layer and going backwards towards the initial state, all the way to the initial state, selecting actions from both action layers. And that's essentially all there is to GraphPlan. When GraphPlan came out in the mid-1990s, it was significantly faster than all the previous planners. And there are a number of contributing factors why this is the case, and I shall point them out to you while we go through the technical details of the planning algorithm. In the second part of this week, we'll be looking at advanced heuristics that can be used for state space forward search, a technique that we've seen in week 2. And in this context, we'll take a closer look at the FF Planner, which was developed by Jörg Hoffmann. And one of the distinguishing features of the FF Planner is that it uses a relaxed problem heuristic, which is on the one hand efficient to compute and on the other accurate. And that will end this week.
And now let's dip into the technical material for week 2. At the end of this, you should be able to implement an almost state-of-the-art planning system.